Okay, so I'm going to start, I guess, with a couple, pretty simple questions, just like I started yesterday. What is synchronous speed?
Is the magnetic field rotation of the magnetic field speed.
Right, Jasper, it's the speed of the rotating magnetic field produced by what? What's it produced by? What makes this rotating magnetic field?
The induced voltage?
No, that it doesn't. No, that has nothing to do with it. The induced voltage in the rotor, if that's what you're talking about, that has nothing to do with what makes this rotating magnetic field. What produces it?
Torque?
No.
Torque. Magnetic field produces the torque, right? Yeah.
Right. That rotating magnetic field produces a torque in the rotor. That magnetic field is produced by the stator windings, those three windings on the stator, the three-phase windings. When you apply a voltage to the motor, the instant you apply a voltage to the motor, those three windings on the stator will produce this rotating magnetic field, right? And it rotates at a certain speed that we call synchronous speed, depending on the frequency of the system and the number of poles the motor has. That formula is 120 times frequency over the number of poles, so it gives me synchronous speed. What's the one other thing that's important to remember about synchronous speed, the speed of that rotating magnetic field? There's one other thing that's kind of important to remember about it.
It's always larger than the rotor speed.
It's always quicker than the rotor speed.
Yeah.
For sure, that's one thing it is. Yeah, it will always be quicker than the rotor ever turns. And the thing I'm thinking of, sorry, go ahead.
It's constant and a uniform speed. We can say the constant magnitude. Yeah.
Right. The minute that we apply voltage to that motor, if it was a two-pole motor at 60 hertz, that rotating magnetic field would turn at 3,600 RPM all the time. It would never change until you shut the voltage off to that motor, and then it just dropped to zero. So it's one set speed that's constant that it always turns out to, right?
Yeah.
So that's good. Good to remember for synchronous speed. What is slip? And again, this is on the first couple pages of that second module. What is slip?
Slip is the span from the one coil to another.
Say that again, Jaspreet.
It is a span from the one coil to another.
Slip?
It is the difference between synchronous speed and
rotor speed.
Rotor speed.
Right on. That's what slip is. It's the amount that the rotor is behind synchronous speed. So if it's 30 RPM behind, that's the slip. If the slip is, or if the synchronous speed's 1800 and it's turning at 1770 RPM, then it is slipping 30 RPM behind synchronous speed, right? That's what slip is. It's often given as a percentage too. On page 3 in the module, you have that formula for percent slip, which is just synchronous speed minus rotor speed over synchronous speed times 100. So then what I want to do is I want to bring up this rotor chart again, just mention a couple things from it. So I got to change.
Yeah, so Brian, I want to.
Yes.
Brian, when you start the rotor chart, I would like if you first show up which side we consider the lower slip and which side is going, like which side to which side is going increase and which side to go decrease, and where is a full load we consider and where is it no load we consider. I am a little confusing about the rotor chart.
Okay, you bet. Let me show you. I just got to move a couple things here. Got to move this over here. And are you guys seeing the, let me just bring it up here. Are you seeing the rotor chart now?
Yeah.
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 And again, I can make it bigger, but is it okay this size? Can you read it okay?
Yeah, that's fine.
Yeah, that's
Yeah,
fine.
Okay. I think the first thing that I want to point out is, I think the first thing I want to point out is if you look at percent slip on the left-hand side, if you look at that percent slip and we start at 100% slip, that is, if it's 100% slip, that means the rotor is not moving. That is the point of startup for our motor we always talk about. So if we
So
say,
that's the low. So that's the
Sorry,
low
go
side,
ahead.
right?
That
That's
is
the lower.
the load. Did you say?
I say so. 100% slip is the lower side, right?
Lower, like it means at the instant we start the motor and the rotor has not started turning at all, that's 100% slip. And we can think of this motor right now, let's just think of it as not having any load at all. Just forget that it has any load or not. When we're at 100% slip, we're at the point where we just applied voltage to the motor and the rotor hasn't gotten a torque developed on it quite yet and hasn't started turning. Make sense?
Yeah.
That's because at 100% slip, the rotor isn't turning at all. If you look at the slip RPM, like for this motor, a 4-pole 60 hertz motor, the synchronous speed is 1800 RPM. And at 100% slip, the rotor is slipping 1800 RPM. It isn't turning at all. It's turning 0, right?
Yes.
If you go from that point of 100% slip and go down the chart to 75 to 50 to 25 to 6.6, that is the rotor speeding up from a dead stop. So when you go from the top of the chart at 100% slip down to the bottom at 1% slip, we're talking about the motor starting up. Starts at 100% slip and speeds up. And if we didn't have any load on the motor, it would speed right up to around 1% slip, because with no load, when you look at these numbers in red at the bottom left-hand side of the chart, 1% slip is no load RPM. So that's the motor starting up, going from 100% slip down to 1% slip. Make sense?
Okay. Yeah. Got it.
Good. And what do most of the values in this chart do as the motor speeds up? What happens to most of the values in the chart as the motor speeds up? If I look at like voltage of the rotor, XL of the rotor, current of the rotor, what's happening to those things as the motor speeds up?
The voltage of the rotor
Go ahead, Isaac.
go down. The voltage of the
Yeah, the
rotor goes down.
Voltage of the rotor
And
goes down. XL of the rotor goes down.
Go down.
Z of the rotor.
Go down.
Impedance of the rotor goes down. Current goes down. All those values go down because as the rotor speeds up, the magnetic field is cutting across it less and less as the rotor catches up to that magnetic field speed. So because the magnetic field is cutting across the rotor bars less and less as the rotor speeds up, there's less induced voltage in the rotor. There's less inductive reactance in the rotor because there's less magnetic field interaction the faster the rotor turns. There's less current in the rotor as it speeds up, less impedance in the rotor. So most of the values go down as the rotor speeds up. Make sense? There's a couple that don't, but most of them go down. Okay?
Yep.
And one value I should explain that's on this chart we never talked about yesterday is the value on the far right-hand side of the chart is rotor hertz. And it goes down as the rotor speeds up too, but what does rotor hertz mean? Any idea? The definition in the module isn't great. Yeah, I'm not real crazy about the definition of the mod. It's on page 7. But any idea what rotor frequency means? No?
Nope. I don't know how to explain that.
Okay. What it is at startup at 100% slip, when we just applied voltage to the motor, but the rotor hasn't started turning yet, the magnetic field is cutting across the rotor bars at the same frequency of the supply. So if the supply is 60 hertz, the rotor frequency means the amount that the magnetic field is cutting across the rotor bars in hertz. And at startup, the magnetic field is cutting across the rotor bars the most it ever will. And so it's at 60 hertz. It's cutting across the rotor bars at 60 hertz. And as the rotor speeds up and catches up to that magnetic field, the rotor frequency will go down because the field will be cutting across the rotor bars less as it speeds up. So at 50% slip, the rotor frequency is going to be half what it was at 100% slip, down to 30 hertz. So that's what rotor frequency is. Okay, it's kind of a little confusing what that means, but that's what they mean by rotor frequency. The amount that the rotating magnetic field cuts across the rotor bars in cycles per second. Okay. Any questions from that? Okay. Then I'm going to try something really wild here. Just give me a second. Whoops. I'm going to try this. Do you guys see a little different screen now? It's that same rotor chart, but it's kind of crunched in a little bit.
Yep. Yep.
Does that look right? And
Yep.
I think the
Yeah.
biggest thing for me is, can you see this? If I was to circle, let's just circle the rotor RPM at 1% slip is 1782. You see that? Did you see me
Yeah.
circle that?
Yeah.
Yeah.
I am so impressed with myself. I figured out how to get some kind of a marker so I can actually mark on this a little bit. Because yesterday I kept trying to show my arrow, but you guys couldn't see any of that. I am so happy. I don't know how to even put it in words. Okay,
That's good.
so it kind of crunches this screen up just a little bit, but you should be able to see the whole screen still. And all I really want to,
Yeah.
one of the main things I want to point out with this rotor chart is to say, I'm going to just draw an arrow like this. From 100% slip going down this chart. Oh, I like that. From 100% slip going down this chart, what does it mean is happening in the motor?
The motor speed is increasing.
Right. The rotor is speeding up. That's all that's what we're looking at when we go from 100% slip and go down the chart this way, is we're seeing the rotor speed up and seeing what's happening to all the values in the rotor as it speeds up. And that's great. And then, of course, there's no load on that rotor. It's going to speed up right to about 1% slip. And so it'll be really close to synchronous speed with no load on that motor. Now, on the right-hand side, if I draw an arrow on this side, on the right-hand side, if we go... If we go this way up the chart from 1% slip, we go the other direction up the chart, what is happening to the motor now? If we're at no load speed and we start going the other direction, what are we saying generally is going to be happening with the motor?
You're slowing it down.
It's slowing down. Why? Because this is the way to think of it. It's slowing down because what is happening?
The resistance increase, pretty much everything increase. Resistance, reactance, impedance.
For sure. As it slows down,
and
the
load.
magnetic field starts cutting across the rotor bars some more. Like if it starts to slow down, then the magnetic field is cutting across the rotor bars some more than it used to, and it's inducing a bit more voltage in the rotor. It's inducing a bit more voltage in the rotor. It's inducing more current in the rotor. And that's happening when we add load. So the way to think about this chart, when we go the other direction from 1% slip back up the chart, that's what's happening in the motor when we add load. So as we start adding load to the motor, it's going to go from 1% slip and start slowing down. So the rotor will slow down a bit. I'll be at 1.5% slip, 2% slip. What is 2.2% slip in this chart? What's it represent?
Full load.
Right on. It represents full load. So from no load to full load, we go from 1% slip to 2.2% slip. So we don't go very far in this chart, but we go from no load to full load. And this motor has a pretty low percent speed regulation because it doesn't slow down very much from no load to full load. But one step back is full load. Make sense? And did you guys know, I think I pointed this out yesterday, I'll just say it again one more time. It says most induction motors on page 3 in the module says under slip, it says most induction motors, I'm going to say most squirrel cage motors right underneath slip on page 3, from no load to full load, most squirrel cage motors will slip between 2 and 5%. So most squirrel cage motors, their percent slip at full load is pretty low. It's around 2 to 5% slip. And this one happy 2.2% slip. Okay.
So Brian, I have one question. What's the average slip like that? I saw somewhere it's they say 2 to 8%. What's the right answer? Is 2 to 5% or 2 to 8%?
Oh, where did you see 2 to 8%? I've seen that number before too. It might have been in the first module. Right, I've seen both those numbers, 2 to 5% and 2 to 8%. Yeah, you're right. I remember seeing that before somewhere. I forget, just it's probably in the first module under nameplate stuff, I think, maybe. But don't worry about it. I think if you get a question on a test that asks what the percent slip is for a squirrel cage motor at full load, if it goes 2 to 5 or 2 to 8, you won't have both in the same question. Like you won't have both as answers. So either one is probably okay. Does that work, Jaspreet?
It's on page 14. Sort of page 16.
The second module? Of the second module?
Yeah, the second module. Yeah, the beginning of
Oh yeah, it does too. That is so sad. To slip. Yeah, that is pretty sad to me that they do that sometimes in a module. In these modules, they'll give you one percentage and then they'll change it. It doesn't change very much, but don't worry about it. On a question, you'll have one or the other, either 2 to 5 or 2 to 8, and you're in the same, pretty much the same range anyway. So, good point to bring up, though. Okay. So
Oh, yeah, I had that circle too.
of course you did, John.
Yeah, as like what the hell's going on here? Huh.
That's
yeah. Jeez.
Okay.
I'm losing faith here.
Oh, don't lose faith. Don't lose faith. There's only probably, in all the modules put together, all the islands put together, there's probably only about 100 mistakes, I'd say. Hardly any. Don't lose faith. Okay. So if we slow down one more step past full load, if we go to the 6.6% slip, if we're loading down our motor some more and we got to 6.6% slip, what's important about that percent slip for this motor?
That's the breakdown torque point.
Right, which means it's the maximum amount of torque that this motor will develop. In this case, for this motor, and that's always a different value, I think they say it can be a number, I think normally it's a number around 10-20% slip. This is a little bit bad to use such a low percent slip here, but it just happened to work for this chart. But at any rate, it's the point where for this motor we have maximum torque. And how do we know that we're at maximum torque at 6.6% slip?
power factor is
Um,
0.707,
Yep.
and
when
resistance and reactance is equal.
Exactly. The R and the XL are exactly the same number. At 100% slip, the XL is a lot bigger than the R normally. The R never changes. It's always a set value. So the XL in a squirrel cage motor is often quite a bit higher than the R. And then as the motor speeds up, it gets to a point and the XL drops off. You'll get to a point when R and XL are the same value. When you're at that point, your power factor of your rotor is 0.707 and you're at maximum torque. And what column on this rotor chart represents maximum torque? What chart is closest in representing what torque looks like in the rotor?
I in phase.
Right on. It's this I in phase piece right here. Whoops, this I in phase. And notice how, of course, this number is in red. And notice how the in phase current in the rotor starts at a fairly low value at startup, increases maximum, and then drops off at the end. So when we start adding load to the motor, if we're at no load slip and we start adding load to the motor, we go from no load to full load. The in phase current, or active current they call it, that current increases. From no load to full load, it increases again until we get to maximum torque. And if I was to add some more load at maximum torque, does my in-phase current or torque increase now? When I'm at 6.6% slip, if I add more load to the motor, does the active torque go up?
No.
No, it goes down. And the minute, if you're at maximum torque and you add any more load to that motor, it's going to stop, come to a dead stop. Okay, so it's good to know maximum torque from this chart as well. Okay. Now what I want to show you is, yeah, I want to show you this chart right here. Will it show my chart? Oh, look at this. Is this torque curves what you're looking at now? Please tell me it is. On the screen, you guys seeing torque curves?
Yeah.
And not the
Yeah.
rotor chart? Oh, thank you. You're making me nervous. You guys are slow answering. Okay, on this is what, I guess you could say this is what engineers often look at for a squirrel cage to see if it's going to have the proper torque characteristics that they want for a certain load. And if you look at the design B1, this one, yeah, this design B1, one that kind of goes, I don't want to draw a line right along, but it goes that one there, right? That kind of colored in blue a little bit. If you guys see that blue?
Yeah.
That design B1 is what it's the most common rotor design that squirrel cage motors have. And so most squirrel cage motors develop torque like this and if you look at the left-hand side at the start of the torque curve, that's from a dead stop coming up on the right-hand side. If we were at 1% slip, or 99% of synchronous speed, you can think of this horizontal part of this chart as if it's percent of synchronous speed, that means the rotor is speeding up from 0 up to, and at no load, it'd be at 99% of synchronous speed, right? If it was 1% slip, we'd be at 99% of synchronous speed. So this is what a typical squirrel cage torque curve looks like. And it starts off at a little lower than maximum torque, comes up to maximum torque, and then drops off at the end. And this part of the chart right here, let me just draw a little drawing. And let's say, yeah, if I'm at 100% of full load torque, right here, this point right here is rated torque, is full load torque. I can draw, I don't know how good I can draw this, but let's see if I can. That's, whoops, full load You don't have any idea how hard this is to draw, these letters. It's ridiculous.
Yeah.
We're at full load torque right here. if you ever see Terry's PowerPoints, some of the writing he does in his PowerPoints, I'm like, holy crow, I can hardly understand what you're writing there. But he's doing it sort of the same way. He's writing it on a screen, and it's a little tough to do.
Yeah.
Correct. Yeah, that's true.
So at full load torque, that's 100% torque here is full load torque. And so when we're looking at a motor from no load to full load, we're actually looking at this little piece of the torque curve right here, just this little piece. As it slows down from 1% slip, from 99% of synchronous speed to, say, 97%, if I was at 3% for full load, this is the part of the torque we're looking at as we're adding load to the motor, and we're backing up this chart a little bit from 100. As we're backing up this chart a little bit when we add load, then the rotor just slows down a little bit and we get lots more torque. This curve is pretty steep at the end here, which means that I don't have to slow down very much to get lots more torque. Does that make sense how that's working for design B?
Yeah.
And of course, at full load torque, that would be at the rated values for the motor, because all the motor nameplate values are for fully loaded motor. So the current of the motor, what other things are on the nameplate? The current of the motor, the torque of the motor that they're showing here, the speed of the motor. The speed on that motor is full load speed. So if it was an 1800 RPM motor, you're probably around 1740 RPM when you're at full load. So these values here where I marked full load torque at, that's full load for that motor, right? Make sense?
Yeah.
When you look at this torque chart, then one thing to kind of make sure you understand from this torque chart too, for design B, when I'm at full load torque, if I added more load to the motor now at full load torque, would the motor stop or not? Would the motor continue to provide torque, or would it stop? If I was at full load torque and I added more load, when you look at design B, what's going to happen?
It's going to stop.
Well, I hope somebody disagrees with Isaac.
No, it'll slow down.
Right on. If I'm right here, Isaac, when you look at full load torque, if I'm right here and I add some more load, the motor is just going to slow down. Like the motor's just going to slow down a bit more. But as soon as it slows down, it just provides more torque again, right? I add a bit more load, it slows down some more. So now I'm overloading the motor. That's true. I've overloaded the motor, but according to this torque chart, I'm not even close to the maximum torque, which is way up here, right? I'm not even close to that yet. So if I overloaded that motor, it would just slow down some more and give me more torque. And that out in the field is what we want to do. Most motor manufacturers design the motor so that it will provide more torque than rated torque. So if it's like a 5 horsepower motor and would give me 5 horsepower worth of torque, if I loaded that motor past 5 horsepower, if I loaded it to 7 horsepower, 8 horsepower, it'll just slow down some more and give me more torque. It tries to turn any load you put on it. But what's going to happen here, we're overloaded, so the one thing that should start to happen is it'll draw more current than it's rated for too. And if it draws more current and we leave it loaded at, let's say I load it to this point right here. I'm about, 7, 8 horsepower. If this is a 5 horsepower motor, you see where I put the dot on that torque chart? If I'm loaded to there, I'm over the rated current. And if I stay there, what should happen after a period of time? And this comes from code on motors. You guys should know about these things for a motor. If it's an overrated current for that motor for a very long period of time, what's the motor going to do?
It will trip, or it will shut off.
It'll trip on what? It'll trip. What it'll trip on though? Overcurrent, overloads. What's going to trip on? Or overcurrent device or overloads. What's going to make the motor shut off?
I think it's going to overheat.
It will heat up a bit more than it should, and it'll trip the overloads, John. It'll trip the overloads in that motor because they're set for a certain amount of current, and if it sees more than that amount of current, if their solder pot overloads, it heats up that solder, and then it causes the overload to trip and shuts the motor off. So if you left it overloaded for a long period, fairly long period of time, it'll trip on overloads because the motor's just going to start warming up more than it should, right?
Right.
But as far as the torque of that motor, it'll just keep turning that load forever. If it didn't have overloads, it'd turn that load forever until it burned up, because it's made to provide more than rated torque. So that and the idea is if you overload the motor for a short period of time, for 30 seconds, 40 seconds, and then bring that load back to normal, it should just turn the load and then keep running, is the idea, okay? Hopefully that makes sense. So, and again, if we just kept adding load at this point, just kept adding load to my motor, it would just keep slowing down again and keep providing more torque. It would just keep slowing down and keep providing more torque until I got to the very top of this curve here, this torque curve, until I get to that point. And that's the maximum torque that motor can provide. So if for whatever reason I put a big load on that motor and I get to maximum torque, if it exceeds maximum torque, what's that motor going to do?
It exceeds maximum torque.
Yeah, if I exceed maximum torque, this point right here, if the motor slows down now, if the motor slows down some more now, what do I get for torque? More than maximum torque or less?
Less.
I get less, right? As soon as I get to maximum torque, if I loaded that motor so it was just a bit past maximum torque, well, it can't produce the torque. It'll turn any load it can, but it can't produce enough torque now to turn this load. And so it's going to go down on torque. If it slows down some more at this point, it's going to go down in torque, and that motor is going to go from like 80% speed, if that's the number we're at here.
Yeah.
That's pretty much right. It'll go from 80% speed to 0% speed in about 2 seconds, and then trip on overloads or overcurrent because it's drawing way too much current.
Mm-hmm.
Okay, so a motor will give me more than rated horsepower. Most motors are designed to give more than the rated horsepower that they have on the nameplate. If it's a 5 horsepower motor, it'll give me more than 5 horsepower's worth of torque, but there is a maximum, a breakdown or maximum torque that we can get out of any motor, right? So the idea of it is just to allow the motor to be overloaded for short periods of time if we need to, and then come back to normal and run and keep running is the idea. But if it stays way overloaded too long, it's definitely going to quit. Okay. Now, I'm going to clear off all this ink. That's how easy it is to do it. I love that. This is just fantastic. Now, I want to talk about, the other thing that I want to talk about is comparing a wound rotor motor and, I want to compare a wound rotor motor and a squirrel cage motor, but I do want to talk about one thing first, and that is percent speed regulation. And the formula, I don't think I have it on a slide, but if you guys have your modules out, the formula is on page 34 in module B, and I think we looked at it quick yesterday too. So if you look on page 34 in module B, you'll see speed regulation. And speed regulation is just no load speed minus full load speed over full load speed times 100 to get a percentage for percent speed regulation. And if we look again at a common three-phase motor, this Design B motor, I'll just kind of highlight that one again, the Design B column here. So if we look at a Design B motor, would we say this has a low or a high percent speed regulation? If I said that full load, yeah, if we say that full load is right here, just in line again, this is full load. This is full load. So from no load, which is down here somewhere. I'll just draw a little line for it and say this is no load. So from no load to full load, does the motor slow down very much?
A little, not a whole lot though.
Not very much. I'd say it goes from like 99% of synchronous speed to maybe, if this is where it is at no load for like 99% synchronous speed, it's maybe down to 97% of synchronous speed full load.
Yeah.
So this would have a low, what we call percent speed regulation. It would be a low number. And notice how it says on the top of page 34 when it talks about speed regulation. It says, when you compare two motors with the same number of poles that are rated for the same power output, the motor with the higher full load speed has a lower percent speed regulation and is generally more efficient. So squirrel cage motors, this design B is the most common type of squirrel cage motor. So squirrel cage motors have a low percent speed regulation, or I typically call that a pretty good percent speed regulation. Low is good, I always kind of want to say. So squirrel cage motors have a low percent speed regulation. They don't slow down much from no load to full load. If you used a squirrel cage motor in, let's say you had it running an assembly line in a car plant, and you had this chassis of this car moving along this assembly line, and you wanted it to move along, that assembly line to move along at the same speed pretty much, whether it's loaded down that assembly line or whether it has very little load on it, you definitely want to use a squirrel cage motor because it doesn't slow down much from no load to full load. So that assembly line will always move along at about the same speed. Make sense? Hopefully. Who do I have still listening to me? Jaspreet, are you still here?
Yeah.
John is? Oh, good. I can only see one person, and it happens to be John right now, so I don't know for sure how many I've got, which is fine. So hopefully this helps make sense a bit that a squirrel cage motor has what we call a low percent speed regulation. It doesn't slow down much from low load to full load. Make sense?
Yeah.
Okay.
So far.
Now, so we always say that two features of a squirrel cage motor is it has low percent speed regulation, which is a good thing. It also has low starting torque, which is okay. It's not always a good thing. Notice how the starting torque for this motor is 150% of rated torque. So that means it gives me pretty good starting torque. It doesn't give me max torque because maximum torque is about 175, looks like. But it gives me okay starting torque. It's just that it doesn't give me a real bang at startup if for like a big heavy load, like a crane or an elevator, or a real heavy.
I can see now that makes sense. To
right.
Looking at the other line design.
Yeah, and a wound rotor motor.
How you look at D
is a little different. So for sure, for squirrel cage, we say it has low starting torque, but good percent speed regulation. Is what we always say about squirrel cage motors. Now, wound rotor motors, you could think of design D. That is a rotor design for a squirrel cage motor that gives me torque similar to a wound rotor motor. So if we look at design D, if we look at design D, and I'll just highlight it a little bit. I mean, you know which one it is. It's this one here. So this design D rotor, it starts at 300% of full load torque. So if it's a heavy load, so for some specific heavy loads like cranes, like elevators, if I need really high starting torque, how can I get maximum torque at startup? How can I have maximum torque at startup? How does a wound rotor motor do it? How do I get maximum torque at startup?
Oh, because you have the external resistors to adjust and set that up.
Right on. We have external resistors, and I could set the resistance. I can set the motor up so it sets the resistance to be the same number the XL is right at startup. And if R and XL are exactly the same value, I'm at maximum torque, and I'll be that way right at startup if I have them both set the same, right?
Yeah.
And then if I didn't change in that wound rotor motor, if I didn't change the resistance at all, if I left it at the same value as the XL at startup, what's going to happen is as soon as the motor starts turning, as soon as the rotor starts turning, the XL is going to start going down. And if the R doesn't go down with it, leave it set it where it was, the torque chart you're going to have, it's going to start at max and then slowly go down as it speeds up, which some loads might be fine. As soon as it starts rotating, maybe it doesn't need as much torque to turn that load. It might be fine for some loads, but for other loads, we need to have that maximum torque all the way along as it speeds up. We need to keep it at maximum torque all the way along. So we would adjust the resistance and the XL so that the R and the XL stay the same all the time it's speeding up, and we're at maximum torque the whole way, right?
Right.
And if I show you, I'm going to try something here. I'm going to do this. If I show you this slide, you guys see a little bit slide on your screen now? See the wound rotor motor?
Yeah.
And that's the one difference a lot of wound rotor motors have from this design D, is that as the motor speeds up, we keep reducing. There'll be a what do you call it, a little computer or whatever on that resistor bank, that as the XL is slowing down or going down, the R goes down, so that XL and R stay the same as the motor speeds up, and we're at maximum torque the whole way up until we're less than maximum load, and then of course it slows down here when we're less than maximum load and rated speed or whatever. And yeah, so a wound rotor motor can provide maximum torque the whole way starting up, okay? And a design D rotor for a squirrel cage motor can only give me maximum torque really at startup. I can't adjust the resistance after that. So it'll give me maximum torque at startup, but then it's going to drop off as it speeds up, which might work for some loads. Does that make a difference? Does that make sense how a wound rotor motor, the whole idea of having that resistor bank and the controller is to adjust the resistance to keep R and XL the same value the whole time it's speeding up.
Yeah.
Okay. And if I go, I'll just use this chart again. If I, and so what, I'm just going to say, when you compare a wound rotor motor to a squirrel cage motor, we always say that wound rotor motors have great starting torque.
Yeah.
But they typically don't have good percent speed regulation, because if I didn't change this resistance in this wound rotor motor, it would look more like this, the D chart, and that chart slows down quite a bit more from no load to full load. That D torque chart slows down a lot more from no load to full load than a squirrel cage one does, the B one. So we typically say wound rotor motors have good starting torque but poor speed regulation. They have no load to full load. Okay.
Yep.
So let me see now. Yeah. So for me, really, if I go back to this, if I go back to our rotor chart, that's really all I wanted you to see from a rotor chart. Is it tells us what's happening in the motor or in the rotor. I got to be a little careful. It tells you what's happening in the rotor as we go from 100% slip. As we start it up, we go from the top of the table down to the bottom. And then when we're at no load speed, if we want to see what happens in the rotor as we add load, we're going from the bottom of the table back up the other direction. So it's just good to understand how those tables work, and be really clear too that in your module, when you look at page 10 in your module, if you want to turn to that page quick, table 3, that's the same rotor chart, same kind of rotor chart that I have on this PowerPoint. Be sure you understand that that table is flipped. At the bottom is 100% slip, because if you go slip, you take 1 and make it a percentage. If you multiply by 100, so at the bottom it's 100% slip. At the top is 1% or 0. At the very, very top is 0. But right, so just make sure you understand that table is just flipped in the book, in the module. So if you're looking at the one in the module, just keep that in mind. Any questions from that? No? You kind of get that
I
okay?
do. I do have questions, but I'm gonna wait till you're done before I ask anything.
Yep, that sounds great, John. That's
Yeah,
perfect. Jaspreet, does it make pretty good sense?
Yeah, it's all good, but I have a two question, but it's from the review part.
From the review, okay. When I'm done, do you want to come back at in like half an hour? Like 10:30?
Yeah, sure. Yeah,
And just ask those questions then? Does that work for you?
yeah.
Okay, then don't leave just yet, because I just want to make sure I mention one or two little things yet, and then we're kind of done with the lecture. And any questions you have, I'll kind of start with you, John, and then in about half an hour, Jaspreet can come back. All I wanted to mention is, I think I want to mention, yes, a couple things from the module. Yeah, I guess I should point out a couple things from the module that are going to be good for you to know too. Hopefully you all three have your module out.
Yep.
And so a couple things you can make note of in your module is on page 8. If you turn to page 8, in the middle of the page, it talks about active rotor current. You can write in pencil or pen beside that, you can write same as in-phase current. In-phase and active are the same thing. So active rotor current or in-phase current are the same thing. So active rotor current and in-phase current on our rotor charts are the same thing. On page 9, yeah, I think I better point this out. On page 9, it shows those formulas. Again, you can memorize these formulas, but I think if you understand that rotor chart, and if you know the percent slip that you're at, you can find all of that. If they give you some block rotor values for that rotor chart and give you percent slip, you can find any of those values. Most of these values just come from percent slip times the maximum rotor voltage we're at, let's say. So you don't need to really memorize these formulas if you understand the rotor chart. But on those formulas on page 9, about the fourth one down, it says speed of rotor. Put an X through that formula because it's wrong. It's not the right formula. So if you're memorizing these formulas, that is definitely not right. I think the best thing to write for a formula, if you're going to write one, is to say NR equals, what do we call, just want to check something. NR equals, yeah, if you want to say NR equals NS, that's slip speed, or sorry, NR equals N synchronous, or synchronous speed, minus slip speed. So rotor speed is synchronous speed minus slip speed, whatever the slip speed is.
Morning, Scott.
Did we go to any other page after that?
At page 11, Isaac, I just mentioned all the bullets in the middle part of page 11 are just good information to read because it explains again that rotor chart. Sort of like I did this morning, it's going through the same stuff. So those bullets are pretty good information. Just put a star beside them if you want, whatever. It's pretty good information.
Okay. Any other information that I missed out on?
Yeah. And then the last thing I want to point out, because I think you can spend a lot of time on this and I don't particularly like it, is Objective 2 exercise on page 15. Hopefully not too many of you have already done this, but Objective 2 exercise on page 15. Question 4, you could do it, but I would suggest don't do it because I think it's a tiny bit confusing what they do there. I have to take a look at it again, but I've told classes.
It is. I went through this and I went through doing it the book way before I learned the other way. So I was like using these formulas in the book on that page.
Okay.
So like when I was doing the in-phase current, I was using like IR times COS to figure those all out.
Right.
But instead of just you know, timesing it by the power factor because I didn't know that yet.
Right, exactly.
And it
And
took a long time.
I think it can take a long time, and I think it's a little bit confusing. I just really think looking at a rotor chart the way we did this morning will work just as well. So, yeah, that's it. That's all I want.
That last